Oh, I've said it before and I'll say it again. We are studying some pretty radical stuff. And we're gonna continue studying some pretty radical stuff today with graphing square root functions. All right, so our two learning targets, we're going to graph square root functions the basic old T-chart way. We're also going to translate graphs of square root functions, which is kind of a shortcut to graphing square root functions. All right, so our only vocabulary term for today to know is what a square root function is. It's a function that contains the independent variable in the radicand. So the x is going to be underneath the radical symbol. And the general graph of it, so here's an example. General graph of it kind of looks like this one right here. Very interesting the way they look, and that's what we're going to be dealing with this section. All right, so let's start off with, again, the basics of a square root function. We just kind of showed you it, and looking at the picture underneath it, it says the same thing that we just kind of said there. Square root function is a function containing a square root with the independent variable in the radicand. The parent square root function is y equals the square root of x. So by parent function means that everything else is going to be based off of that and somewhat similar to that. You may have something multiplied on the outside. You may have something added on the outside or added on the inside, but it's all building off of this parent function. So the table and graph below show the parent function square root function, making a t-chart. You can make a t-chart for any function and find the graph. Okay? Sometimes it's hard to know exactly what x values to use, but in this case, if you use 0 on all positives, that shows you what the graph would be. So here's our t-chart. And what was chosen were a couple that were pretty good, like square root of 0 is 0, square root of 1 is 1. Square root of 2, we rounded here to 1.4. And then after that, you can use this 4 and 9, because those are perfect squares, and it'll make it a lot easier. But you see it kind of jumps up a little bit from the start, and then it starts to level off a little bit. That's kind of what a lot of these square root functions are going to look like. So you can graph a square root function by plotting points or using a translation of the parent root function. Okay, so we're going to start just do a little bit of the plotting points part. So um, one part of that is figuring out the domain. Whoa, what just happened there? Not what I meant to do. All right. And remember, domain is simply the x values, or the left to right. How far left it goes, how far right it goes on the graph. And so if we look at an equation like this, we have y equals 2 times the square root of 3x minus 9. We know that the square root, the number underneath the square root, cannot be negative, because you cannot take the square root of a negative number. So we know that 3x minus 9 has to be greater than or equal to 0. That's how you can tell the domain. You're going to start by doing this, setting the part underneath it greater than or equal to 0. Now I'm going to solve it like a normal inequality, and I add 9 to both sides. You're left with 3x is greater than or equal to 9. Divide by 3 on both sides. And you get x is greater than or equal to 3. So the domain of the set of this function is any x value greater than or equal to 3. So now you know where to start your t-chart if you're graphing. We're going to start at 3. You can do 4, 5, 6 if you want. But that's how you can tell what values to use. It's going to start at 3 in this case. So why don't you try this? What's the domain of y is equal to the square root of negative 2x plus 5? So pause it, try it, and unpause it, and check it. All right, so I set the inside part, the part underneath the radicand greater than or equal to 0, because it has to be greater than or equal to 0 for our square root to work. And I found that when I solved it, I got x is less than, because I had to switch the sign here at the end, less than or equal to 2.5. So one thing you'll notice is that means it's going to be going to the left. It's going to be, the function is going to be going to the left. And it has to do with the number in front of the x. We're going to talk about that in just a little bit. But graphing a square root function in general. So here's an example. Here's a real life example. It's actually it says graph the function I is equal to p 1/5 times the square root of p. So that'd be like y and x instead of I and p. But in this case, I is the amperes. I'm not even sure how that's pronounced. For a certain circuit, amps is the shortened term. Um, for a certain circuit with p watts of power, when will the current exceed 2 amps? So we're going to do a typical thing that you would do with a graph, and that would be making a table. So you can tell that if you can take the p underneath that, we know that the domain would have to be p is anything greater than or equal to 0. So we can use 0. In this case, we use 0, 10, 50, 100. All right, so if you plug in 10 for p, the square root of 10 is about 3 point something, and 1/5 of that is going to end up being 0.6. Square root of 50 is about 7. 1/5 of that gives you 1.4. Plugging in 100, square root of 100 is 10. 1/5 of that is 2. So we have some points there that we can then plot on the graph. And you may have to make your graph differently because this one goes up to 100 for the x's, and we don't want to count ones all the way up to 100, so you can label it going up by 20s. And you see the graph looks like that general square root function graph. Slightly different. It's going to start at 0, but well, this says the graph continues to increase after point 100, 0, or sorry, 102. So again, it looks very similar to that parent function that we showed on the graph before. So here's the thing that I pointed out before. If the x value is positive, and by x I mean the number in front of the x, if it's positive, the graph will face to the right. If it's negative, it'll face to the left. So back up here, this is a positive x value. There's no number in front of it, so it's positive 1, so it goes to the right. But this one here, we had a negative 2 in front of it, so it's going to open up and go to the left, interestingly enough. So what I'd like you to do is graph this function, y equals 3 times the square root of x. All right, remember the domain x is going to be anything greater than or equal to 0, so we can start at our xy table, our t-chart, and I'm going to pick 0, I'm going to pick 1, I'm going to pick some other perfect squares like 4 and 9. Nah, 9's not going to fit, but we'll use 9 anyway. So square root of 0 is 0 times 3 is going to be 0. Square root of 1 is 1 times 3 is going to be 3. Square root of 4 is 2 times 3 is 6. Square root of 9 is 3 times 3 is 9 as well. Okay? So when we're graphing this, we know 0, 0 is kind of our start. We have 1, 3, 4, 6, and then 9. 9 isn't going to work, but it's going to kind of go up pretty high pretty fast, and it's going to level off. And the reason it's going up high faster is because of that number in front of the radical. That's making it go up 3 times as fast as the normal parent function would, or as high as the normal parent function would. All right? But that's the graph of that function. So that's basics of graphing square root functions. Using our t-chart, but first finding the domain so you can figure out where to start your x values on the t-chart. Now, you can also use this translating. It is kind of a shortcut to graphing as long as you know what the parent function looks like. And so for here's what we're gonna how we put it. For any positive number k, graphing the function y equals the square root of x, then outside of that plus k, translate the graph of y equals the square root of x up k units or down k units if it was a negative. Oh, here it is. Graphing the square root of, sorry, y equals the square root of x minus k, translate the graph down that many units. So in other words, it's just where it starts. The k value is similar to the b value. So the k value is outside the square root symbol. And I'm going to put here, it's essentially the y-intercept. So if you want to picture like the y-intercept, the b value, as long as it's on the outside of the square root, it is like a y-intercept. So what is the graph of the square root of x plus 2? So we're just going to start the graph 2 up from 0. So when we do that, instead we start right here instead of, right down here. And then it's going to go up ever so slightly. If we're translating it, it doesn't have to be perfect. You don't have to make your t-chart. I want to know the starting point, how the starting point changes. And it's actually very similar to how absolute value functions are graphed. When you have a number on the outside added, it moves it up or down. The parent function of absolute value functions. The same thing's going to work for left to right. So if you look at this one, why don't you try this one? Graph the function square root of x minus 3. Why don't you pause it and try it? It's actually going to be pretty easy to do. Otherwise, you can unpause it and check. So we're just going to start it 3 lower than 0. 1, 2, 3. This is the starting point, and it's still going to have that same general look to the square root function. It's going to be the same as the parent function except for where it starts. All right, now the other way it could change if you're translating it horizontally, left or right. And this is where it's interesting. It's the same as if it was for absolute values as well. For any positive number h, graphing y equals the square root of x plus h on the outside. Actually, this is supposed to be on the inside. Sorry, I must have left out the lines. This is on the inside now. That translates the graph of y equals negative x to the left. Even though it's plus h, it's going to the left, so it's opposite. Whereas graphing this with a minus is going to translate it to the right. Very interesting how it's opposite, just like in the absolute value function, but that's the way it is. So the h value is inside of the square root symbol in this case. So an example would be, how did I miss this again? Y is equal to the square root of x plus 3. So it's inside the square root. So we're going to actually start at 3 to the left. So instead we're starting it way over here to the left. So again, it's opposite. But then the rest of the graph is going to look the same. If it was on the outside, it was 3 up. If it's on the inside, it's actually 3 to the left. So if you look at this one, you can try this one. This is inside. I have it correct now. Y is equal to the square root of x minus 3. And if you look at it, it's a minus sign, so it's actually going to be to the right, 3. And we're going to have the same looking graph. All right? That's the very basic way of doing it based on translating. It's not super accurate because you're estimating what the graph looks like, but it is a good way to change the starting point especially. All right, and that's all you need to know about graphing square root functions today. Graphing square root functions, again, you can use the t-chart or you can use the translating method. So why don't you use that and answer this question, either on your paper or in your head. Can the domain of a square root function include negative numbers? Explain. Is there any way that you could go to the negative, so I have the square function go to the left? We kind of talked about it, so I'll be able to explain that. That brings us back to our learning targets for today, which was to graph square root functions and to translate graphs of square root functions. All right, I hope you got something out of this about graphing functions. We'll see you next time.